All right, now we're going to get into oil well. Before we get there, again, you go from gas to oil. It's a lot easier. I can write these equations in terms of cumulative oil or cumulative gas. Again, remember, the original equations were developed from oil well data. No one ever derived it in terms of gas well performance. And there wasn't any performance that was available to use on an empirical basis. So you can go on through, and the bottom line is in terms of you got a problem now for oil wells. I can define for gas. I can define a gas in place. We saw that from the pressure cume. But now for oil, I have my definition of NPI has got to be in terms of an oil in place times a recovery factor. And well, like for oil, you'd have to run something like a Turner material balance. Has anybody ever run 3240? Program 3240, the compositional material balance? Or the Turner material balance? This is the way reservoir engineers used to do their work before models. It's nothing more than a one-cell model. And what you do would input, you'd input PVT data and the oil in place and so on and so forth, but you'd use different sets of relative permeability. A very poor relative permeability curve is going to give you low recovery efficiency. A favorable relative permeability is going to give you high recovery efficiency. So you have to get NPI for solution gas drive. You have to kind of make a Turner type material balance or a one cell model type of a run, or a recovery factor based on the API equation that some people say isn't any good, but it's better than nothing, or a recovery factor from analogous field. What I'm leading to is the NPI has to be defined by oil in place times a recovery factor. The gas in place, you can do the same thing. And this is where we get away from a PWF only being 0. The G in the equation would be the original gas in place times the recovery factor, where you define it in terms of 1 minus the flowing pressure over the shut-in pressure, if you're going to ignore Z. You can throw Z in there, but then the G sub I is equal to G. The original gas in place times the recovery factor is going to be G. So if you do the matching, you back calculate a G, you know the P sub F, you can get the original gas in place. But you really have to understand that that's how you make the transition from gas to oil. Everybody understands original gas in place. That's a little different. That's function relative perm. That's why you do, why it's clear when you do the derivations in terms of single-phase gas. Because you'd never get there only looking at it from an oil standpoint or solution gas drive reservoir. You'd never understand what's going on. So there was a real advantage for me starting off in the gas department. I worked in the natural gas department for about 10 years, 3 years out in the Texas-Oklahoma Panhandle, and then 7 years in Bartlesville. This is oil well inflow performance. This is the Vogel curve with data off of Vogel. He built a model and he ran a bunch of cases for different types of PVT properties and different solution gas drive reservoirs, and he come up with an inflow performance equation. Q over Q max is equal to 1 minus 0.2 the ratio of PWF over PR bar minus 0.8 times the ratio of PWF over PR bar, that expression squared. When he presented it in dimensionless form, and being in the gas department, we had a dimensionless form of the back pressure equation that we used to size orifice plates when we were running multipoint tests. And when I saw his paper, immediately it became apparent to me that what he's saying is that oil wells should behave just like gas wells. So I went out and got a bunch of data, including some on Ecofisk, and sure enough, when you plot the data up, it plots as a difference in pressure squared. As a back pressure curve plot, the shut-in pressure squared minus flowing pressure squared versus Q. And it's a straight line on log-log. And this is a form of an oil well inflow performance. The slope of 1 is very close to the Vogel equation. So if you use this or Vogel's, you get about the same results as a production engineer. But as a reservoir engineer, I need to do more. In this form, see, I dropped the 1 term, and the coefficient becomes 1 for the squared term, and the other coefficient becomes 0. Now I have a back pressure equation where, like I said earlier, it's not, the rate's not strongly a function of the level of the flowing pressure that I'm going to choose. So that's one advantage that I have in knowing it behaves like an oil well, or like a gas well. Well, the circles, or well, the solid line here are the results out of the one simulation model. The simulation model results that Vogel published in his paper. And these are the match points that he referenced. And if you draw a line through a match point A and continue as a straight line, you know, this would be the productivity index expressed in terms of a difference in pressure, I delta P. And you'd indicate that that well flowing at that rate, at whatever flowing pressure that is, has an absolute open flow potential of about 330 barrels of oil per day. If you take his inflow performance equation, which is a dotted line here, and say that the absolute open flow potential of that well is about 195 barrels of oil per day. Now, if you take this form of equation and use it, you'd get the circles, and that shows that you would get slightly less. For practical purposes, there isn't much difference in the answer here, but conceptually it says that the delta P squared form equation fits better his reservoir simulation model than his empirically backed out inflow performance equation. You know, so from a production engineering standpoint, well, there isn't much difference, but again, you also see that at different stages of depletion that this curve continues to move. And again, the delta P squared fits all the way. It's a better representation of the inflow performance. If you take the results of his model and the results of a paper published a long time ago by West Garvin and Sheldon of Exxon, the very first computer solution, a simulation computer solution of a solution gas drive reservoir, you end up with exactly the same type of results that I'm going to demonstrate here. To include the effect of the relative permeability shift, you know, the curve would be like this at initial conditions. As you deplete and the saturation of the oil, you start to decrease. The relative permeability effect is going to be that you would have a sequence of curves that would be shifting constantly to the left, just because of the saturation changes. Okay. You don't have this in the gas well. The relative permeability is always equal to 1 in the gas well, so you don't have that shift. You can approximate that shift with pressure depletion by multiplying the delta P squared term by the ratio of the shedding pressure at any time to the shedding pressure at the bubble point pressure. You got to go below the bubble point before you start building up saturation to get a shift due to relative permeability. If you take all of Vogel's data that he published, and even that other paper, and you use this form of equation, all of those curves that were shifting down with depletion can be represented by a single back pressure equation that includes the effect of relative permeability. And again now, see, I've got a back pressure equation now for an oil well. It includes also the migration of the performance curve with depletion. Yes, so I use that and the material balance equation to be able to derive well, this is to show you the comparison. This would it'd be Vogel's IPR. This would be the delta P squared IPR. This would be a delta P. And what we found out from real data on a bunch of oil wells in the States and even within the ECOFISC is that the N value is less than 1, and if it gets less than 1, the relationship gets even worse. The effective drawdown on flow rate. You get less of an increase in flow rate for a given drawdown as N value increase, or it decreases in value, where with a limiting case would be 0.5 again, which is exactly the same range as limiting values for gas wells that you find for oil wells. And again, field data demonstrates that to be the case. In lieu of ever running any multipoint data, just use an N of 1. That'll at least give you the same type inflow performance relationship as you'd get if you use your Vogel's curve. I took different forms of material balance equations. This is what I get for solution gas drive. There's the rate equation, there's a material balance. We looked at it both as a linear form, as a pressure squared term, because of the solution gas drive. You're not going to, a totally undersaturated system is going to be linear with cumulative production, because the gas is evolving in a solution gas drive system. You're going to have a curvature, and we express it that way. You can derive the exponential solution, the hyperbolic. You can define the B value in terms of N, and the D value in terms of N for an oil well. Remember, the NPI is oil in place times the fraction recovery. And that's a function of the relative perm curves that you would use for the system. There's a set of ARPs, relative perms, for sandstones and carbonates. He calls them minimum, average, and maximum, and we've got that in some of our programs. The Turner material balance has that set in there. For a given set of fluid properties, you can input in the program. You can select these different relative perms, and you can get some type of fraction recovery to use for inclusion in your rate time. But you find out for an N value 1 for the oil well back pressure equation, an expected value B for solution gas drive would be 0.3. Okay, that's for what I would term probably an average relative perm set of curve. For a very poor set of relative perms, you're going to get lower recovery, so the B value has to be less. So B value approaching about 0.1 would be a reasonable number to use for a poor set relative permeabilities for a solution gas drive reservoir. So there's a way of selecting the value of B as a function of recovery efficiency, or implied recovery efficiency. We're going through the same thing here that we did for gas. I'm not going to dwell on it, other than we're following the same logic. that we did for the gas well example, but now we're doing it for oil, and defining the D sub I in terms of these variables. Nothing more than the same thing, but for a different set. A pressure versus cum that would be more linear than the other one. We're starting to get into now. This is the type curve equation, or the dimensionless solution for the ARPS equation. You know, for rate time equation, this would be for any b greater than 0. This would be for b of 0. That's nothing more than exponential. And the way that I generated this curve really is I set the d sub I of 1 and the q sub I of 1 for various values of b, and I was able to get all the accepted ranges of the decline exponent on a single log-log type curve, log-log curve. And the whole concept of dimensionless curves, or a type curve matching, is to plot the data on the same scale as the type curve on tracing paper or regular paper, and then go to the photocopy machine, get a transparency. It's easier to look through a transparency than it is a tracing paper. Or like in Bartlesville, we've got Mylar that we can plot the data on. And if you're looking at a whole bunch of wells in the field to see if they all overlay each other, if you plot each one a different color, it's easier to see each well individually as you're trying to construct one master curve, or to see if all the wells in the field ought to overlay each other or not. You know, that's a diagnostic tool that you could use, overlaying each other. I had mentioned to you earlier, there's a region out in here where all these converge, and if your data existed in that region, you can't tell if it's a 0 or a 1. But you can throw it in a computer program and do a statistical regression. It would give you a theoretical best fit. It'd give you any answer between 0 and 1, but that don't prove that that's what it is. You know, that's one of the dangers. Your data has to get down in the area where it starts becoming unique, where it won't fit any place else for it to be the correct answer. We showed the ranges, like for a solution gas drive, an expected range of B would be about 0.3. A very inefficient solution gas drive would be in a region between 0 and 0.1. A gas well, a full water drive, a gravity segregation, that solution has been derived a long time ago by some fellows from Shell. All of those systems, even with a maximum recovery, single layer system, you can never get in excess of a B value of 0.5. You know, so it wasn't until we start to get into understanding from rate time data, layered no cross flow system, that the region between 0.5 and 1 can best be described by layered no cross flow reservoir behavior. So this now becomes a diagnostic tool. And as you get higher and higher in the value of B, it tells me what the ratio of the high perm to low perm layer is. I know that from decline curve analysis. I can get there. You know, this is the power, really, of understanding the concepts and being able to use them, even though you may be involved in simulation. This range out in here is telling me I'm into layered no cross flow. You know, so it wasn't until we start to get into understanding from rate time data, layered no cross flow system, that the region between 0.5 and 1 can best be described by layered no cross flow reservoir behavior. So this now becomes a diagnostic tool. And as you get higher and higher in the value of B, it tells me what the ratio of the high perm to low perm layer is. I know that from decline curve analysis. I can get there. You know, this is the power, really, of understanding the concepts and being able to use them, even though you may be involved in simulation. This range out in here is telling me I'm into layered no cross flow. And yeah, the difference, I'll introduce it now. At t equals 0. I keep forgetting that I'm not tied to a cord. If I was to make a rate time plot, either to use these equations or to run a model, normal values of b, with the worst case being exponential, that's going to be my rate time plot from t equals 0. The b value that is high, and this can even be semilog, the b value that's high is going to give me something that's going to come down like that. And this difference is substantial in the early times, and it has a dramatic effect on your economics. Production for people are thoroughly confused because everybody says exponential is conservative and hyperbolic is optimistic. Well, the difference here is we're starting at q equals 0, or t equals 0. You know, this is going to be my q sub I. What people are normally working with is field data. When they make that statement, you know, if the field data in early time is coming something like that, if I extrapolate exponential, you know, this is going to be b equals 0, or if I extrapolate hyperbolic, you know, this could be b equal 0.7. There's a big difference. You know, so we ran into this with one of our co-ventures when we were looking at the field we were going to develop in China. Our co-venture is saying, no, they're using exponential, that's conservative. We said, no, that's optimistic, because we were starting at t equals 0. We couldn't convince them. It makes a big difference whether you're starting with your performance data and extrapolating exponential or hyperbolic, or if you're using exponential or hyperbolic to start with your basic data at t equals 0. So you people that are working on prospects, if you think exponential is conservative, it isn't. It's optimistic. Because you're projecting a higher rate early than you what you would get if it were hyperbolic. And hyperbolic gets back to, that's what you get if it's layered no cross flow, and you're obligated as a reservoir engineer to run both cases. A no cross flow case and a cross flow case. Well, let me show you now, that just kind of introduce you to the problem. It's an actual gas field that we developed in Canada. They made their forecasts, and it was basically being done with the assumption that all the gas was there, and we drilled 4 wells, we had the deliverability nailed down, that we were going to produce for a period of 7 years at a constant rate, and then we were going to go on decline. And then say, well, let's look at risk analysis. This is a new tool. Management wants to see risk analysis. This makes it, this gets the monkey off our back. Okay, we've done a risk analysis. So they vary aerially the porosity, the thickness, the water saturation, and all that jazz. And then they say, well, if we do a risk, the worst case with risk is going to look something like this, let's say. Okay, this is the, or the risk case. The worst case. It turns out it's a layered no cross flow reservoir. Do you know what the worst case was? It went less than a year and then dropped off the end of the tape. It was a disaster. Could have been predicted at the beginning. And you could match this performance by using the existing livability and cutting the gas in place to about 50 billion. If you use layered no crossflow, you get the deliverability of the wells are exactly as predicted at the beginning, and the gas in place is exactly was mapped geologically. It was 100 billion. The report was prepared by Schramko. It was distributed. He went to make a presentation because he was working on it for a while when he was transferred up there to Calgary. And he made all this presentation and everything fit beautiful. Co-ventures were really impressed when he got there. They got the results of some production logging tests. And on the shut-ins, they were backflowing during a shut-in, which is an indication that there was differential depletion in backflow. So that the layered no crossflow reservoir. So this is very important. You couldn't come close with a standard type risk. This is the risk. This is the base case as far as I'm concerned. And you're going to get arguments from people and say, but I don't know how far the shales would go or this or that. That's not the issue. Assume that it is. Like for the Guyman-Hugoton, you're looking at a field maybe 36 miles wide and about 30 miles up to the north, and I don't think you would ever, even after all the wells were drilled, be able to demonstrate for sure that the shales are continuous across the whole field, which they are. All of Kansas, all of Oklahoma, all of Texas, even into the West Panhandle. It's all layered no crossflow, over 70 trillion cubic feet original gas in place in that area, and it's carbonate. And you're looking at the present time, you're looking at your 300 pounds in Harrington and about 100 pounds in the Crider, the differential depletion. We've done all those studies, and we were able also to demonstrate that if you take the rate time production performance in the Texas Hugoton, which was produced faster than it was in Oklahoma or Kansas, it started on decline in the 70s. We went about 7 miles south and looked at over 30 sections, which is one well per section. All the wells have B values of 1. Layered no crossflow. I'll show you some of the recent layer pressures that we got, where you're looking at about 200 pounds in Harrington, and I think 70 or 80 pounds in Crider. Now to this day, after producing for over 45 years, the differential depletion that exists. After 45 years, if there was any crossflow at all, it should have equalized, but it didn't. Now, I like to kind of introduce this to demonstrate again the concept we talked about earlier about recovery efficiency with drive mechanisms. For a totally undersaturated system, normally normal pressure ranges and what have you, you're going to get about 5% recovery. Your solution gas drive about 20%. As the gas cap gets larger, you can get higher and higher, and water drive you're going to get, you start getting a range of 40%. Again, conceptually, every well, regardless of what type of drive mechanism it's ultimately going to develop during the transient period, it's got to start at the same place, at the same QI, get T equals 0. And the only way I can get to higher recoveries is to go down a larger and larger value of B. This would be exponential. This would be maybe 0.2 or 3, and this is getting in the range of about 0.5. So the value of B starts reflecting recovery efficiency. And then you run into problems, say, well, but what about when you get into layered no cross flow, that you can get in excess of 100%. Well, if you reference the recovery of the more permeable layer, even that type of thinking still holds up, okay? Because in a lot of these cases where you have layered no cross flow, the high perm layer is carrying everything. If it wasn't for that one, the whole project wouldn't be economical in the first place. And a low perm layer is gravy. You know, so you can tack that on, and referencing to the gas in place in the high perm layer with a B value that would be large enough, you'd get a higher recovery than the original in place in that layer. Is another way to look at that. We took program 3240, which is compositional material balance, that's available within Phillips. And all we're trying to demonstrate here, we ran it with the ARPS, a minimum relative perm, the average relative perm, and the maximum relative perm, ran the same identical case, same fluid properties, everything else, the same in place. And we made a rate versus time. And you can see initially, even before you start evolving gas might, everything overlays. And you keep coming down to lower and lower projections in the early time with the less efficient relative perm curve. You know, so this again is nothing more than to give you the idea of the B value reflecting recovery efficiency. We ran this case kind of as an extreme case to also demonstrate it in terms of in undersaturated reservoir. This is where it would be extrapolating to, and these are the other two relative perm, the minimum and the average. This recovery factor would be about 1.5%. This would be 13% for a minimum and about 22% recovery factor for the average relative perm curve. One very fundamental concept. There's a lot of papers being published now in terms of a pseudo time, where in essence what they're doing is they're doing a material balance on a one-layered system such that they're updating the total compressibility of the system, or in reality, like for gas, the gas compressibility. That the gas compressibility isn't a constant, it's varying with pressure. And fundamentally, it's the variation in the compressibility that causes the B value to go from exponential to some other value higher. That what they're doing by introducing a pseudo time in working a material balance and updating the compressibility, when they do that, they drive it to exponential. And the only advantage of exponential is say, well, if I have exponential, then I can rigorously use the superposition. But I got lots of problem with that. As long as I know that the B value is a reflection of the changing compressibility with pressure, I'd rather use B value, because you don't give your production forecast to management in pseudo time. You give them in real time. And where you're going to really get into a trap is how do you work a material balance on a 2 or 3 layer system, because you have no data to be able to define what those would be. And that's easier to define in terms of the B values themselves. You know, a 0.4 plus a 0.4 adding up to a 0.8. And I don't know what obviously an exponential would be another exponential, but I don't know how you work a material balance on 2 or 3 layers. You just don't have the data to do that. So it's nice to pursue that from an understanding basis, but that as far as applications, you start running into real problems. So I'd rather run into it in terms of the real values of B. I introduced this, or I've left this out of a lot of my recent presentations, but I think I was preparing to come over here. I ran across this because I had to go through all my overheads and try and get them all together for the various topics I was going to discuss, and I run across this one that I'd failed to use earlier in some of my presentation. It's nothing more than a log-log plot of rate versus time for a primary decline on a carbonate reservoir in West Texas. I think it's the Clyde Cowden. It's in the field case history paper. In a secondary decline, reinitialized exactly overlays the primary. A real good approximation is your secondary value of B is going to be the same, very close to the same B exponent as your primary. And you can really start understanding this more when you get into layered no crossflow. What you have in layered no crossflow is you have the high perm layer contributing first. That's where the majority of production is coming from. And then you deplete that, you virtually deplete it very quickly, and then your low perm layer is contributing the majority of production. It's real easy to see. If you get into water flooding, you have the same thing. Your displacement is going to occur in your more permeable layer first, and your other layers are going to kick in later because you're just not going to get the water in there. Okay? So a good approximation is whatever B value you get for primary should be an expected one for secondary or even tertiary, because the logic is the same. You know, if you have a good relative perm for primary, you're going to have a good relative perm for secondary usually too. You know, even for a single layer system. Isn't it interesting that they do overlay? When you go back and start looking at a lot of the water flood papers that are published in literature, I have found none that ever included any of the primary production data, so that how I could use this performance data to help to verify this. But he had it on the Clyde Cowden. A lot of water floods too, there's an increasing rate period, so you may not you be far enough into a decline to have it available. But almost in no case have I been able to find any primary production data to indicate what the B value was there. This is what we call a type curve plot for the constant wellbore pressure solution that's used in drawdown in buildup analysis to get KH and skin, pressure buildup approach to reservoir engineering. Defined in terms of a dimensionless pressure and a dimensionless time. If you plot your data on log-log paper, the same scale, you should be able to move the data around on this plot until it matches somewhere along this curve. Then from that match you get match points, and you can calculate the KH from a match point of delta P and PD, and from TD and T you calculate RW squared, which is RW prime, and that's where you get your skin. Yeah, so this is the whole concept of the type curve in pressure transient analysis. Was originally when we got the EcoFist data, I called in Ramey. I think he was at Texas A&M at the time, and we worked together in an office in the Adams building in Bartlesville and developed the type curve approach for analyzing EcoFist data. You know, the example in their published paper is the EcoFist 242X well, DST 7 or 8, I think it was. But you know, there's a lot of background to the EcoFist in this from a standpoint of even rate time analysis. I'll show you one of the ETA wells. You know, but this is the constant rate solution, and there's an approximation you're going to see later. You know, you just turn it over, and that's the constant wellbore pressure solution. Except instead of going down a 45 degree here at pseudo steady state, you're coming down an exponential. If your data can never go up one of these stems on a build-up, but on a drawdown, an extended production test, if you went up one of these stems, that's called a reservoir limit test. That is really the definition of a reservoir limit test. And that's what it is when you go into depletion on your rate time. If you're going down a depletion stem, you can define the pore volume or the in-place of either oil or gas. During the transient period, you can get KH and skin, like for the build-ups or drawdowns, and for the rate time analysis during the transient period, you can get KH and skin. But you have to go down a depletion stem. You have to be able to get in place. This is an example of one of the Ecofisk wells. Actually, 1981, the Ecofisk B24. Pressure buildup data. These are the points that were plotted on a tracing paper originally, where the tracing paper is moved over to where it overlays a scale, and we used to just plot with the data with the tracing paper actually taped to the type curve. We'd plot the data, you take off the tape, move it around until we got a match point. You know, this represents the tracing paper here. This is the type curve. Once the data match, you just get a match point. This point here was the match point at a time of 1 hour. You could read a TD of a 0.34, and at a delta P of 100, you get a PD a 0.23. You substitute your PD, your delta P, you know the Q, the mu beta from PVT, and you calculate KH. From your time match point, you have the time, or the TD, you know the K from the build-up, actually KH. You don't even have to know the H. You know the KH from the build-up, and you substitute that in here, and you calculate the half fracture length here, or the skin. What it turns out really is in the denominator here, you got the KH and you have phi-H. The H is canceled, but actually the phi-H, that's the in-place number. The porosity times the thickness is really defining the in-place. So that when you cancel that out, you thought you were, when you pick the H, you just determine K. Isn't true. When you pick the H, you're determining in-place. And again, makes no difference when you're doing these kind. But when you go into production forecasting, I guarantee you get a lot different answer if you assume the oil or gas in place is a half. One assumption. Okay? This is just to try and demonstrate to you that the basis of log-log type curve matching is that the unit solution, the type curve is based on solving for a dimensionless time of 1. You know, to where you can run the model and set it up, the variables, such that all of these in there is equal to 1, all of these here is equal to 1, and the answers you spit out you can plot on log-log, and that's your PD-TD. So every well in the world, regardless where it's at, is going to look just like the analytic solution, except it's going to be different by these coefficients. And that's going to be the shift. That's the shift that you get in the data from the type curve. These sets of variables here, the KH in PD, in mu beta, and in TD, the K, and the porosity, and the skin, and so on and so forth. This gets back to what we tried to show you before. In QD is nothing more than PD, but the reciprocal. Okay, that's nothing more than the reciprocal of that, but we substitute delta P instead of Q. So the form's identical. We showed you before those three fields in the East Texas field that were, they'd all overlay each other, but they were displaced on the axis in the X and Y direction. Well, this was, well, actually this one and this one, the reservoir variables were different, but they all looked the same. And it's a universal solution. It isn't just, because we've solved a problem in the Oklahoma-Hugon doesn't mean that conclusions and results that we get aren't applicable to the Ekofisk area in Norway. Because everything, all the concepts are based on dimensionless concepts. You solve, see, this is the advantage of looking at the solution of an, if you just looked at these equations in equation, which is normally what we're doing now that we've computerized the world. You just stick it in a computer and you press the button. You get out answers. But if you plot some of these solutions in graphical form, and if I take data and I plot it, like the back pressure curve or the rate time log or the pressure time log, I can see what the analytic solution looks like, and I can tell whether I'm in a transient or in the semi-log period or in a depletion period by looking at the data. If I don't make those plots, I'm looking at equations, I can't get there from here. You can do the same thing with regard to the ARPS equation. It's in dimensionless form. I solved it for a D equal 1 and a QI equal 1. And this is the same logic for the ARPS curve. You plot the data, just like you do for a pressure drawdown or a pressure buildup on log, and you move around the curve until you get a match. You get the match points, and you can calculate the Q sub I and the D sub I and the B. Now we got an extra match point on the ARPS curve. We're not only calculating from dimensionless time. In dimensionless rate, we have a B value that we also match. That gives us a third match point in a sense. The concept of superposition, I learned the idea of superposition from pressure transient analysis. And if you go into the monograph 1, pressure buildup, there's some examples worked out there in detail with the equations and some sketches of the idea of superposition. The idea of superposition is nothing more than every time you introduce a transient in a problem, you go back and retrace the QD TD or the PD TD. That's all it says. And well, the old perturbation goes on into the future. Now I've introduced a new one, and I just added on to that one, and that's the superposition in terms of pressure with a change in rate from Q1 to Q2. This is the arrangement of the equation, and you can continue on forever. A delta Q over a delta time period. Use exactly the same logic with regard to rate time, and where it starts to come into play really is when you're dealing with the lower permeability systems, but it also comes into play at higher permeability, which we'll get into later. But here we're looking at a change in flowing pressure and a change in rate. This rate from the original flowing pressure goes on into the future. In a delta change in pressure, I go back and retrace the QD TD, and I add that delta Q onto this one here, and that's the idea of superposition. Well, the people that are attempting to go into the pseudo time says, well, I can get more rigorous superposition into my problem if I introduce a pseudo time, but if you go back and relook at the QD TD for the ARPS equation, there's a long period there, whether it's exponential or a BO1 where it basically overlay. That's normally the interval of superposition you're interested in anyway. Okay, so it really don't make that much difference. The interesting thing is if you really look at data after a shut-in, you're going to get a transient spike. I know it's used here in Ecofisk area. They've done calculations. Some people refer to that as a flush production or the ability to make up production because we were shut in. And you'll see the transient spikes when they bring the field back on after being shut in. Low permeability stimulated wells. The interesting thing is if you ever see a reduction in flowing pressure, you know, the limiting case of reducing the flowing pressure is a shut-in. With a superposition, changes in sign, and you'll really see data where you have a curtailment by cutting a well back with a choke, where the rate's going to drop down and then it's going to come back again at a higher level. Exactly the inverse of increasing the flow rate due to a choke. So that when you look at the data, it looks like spurious data, like it has no meaning. In reality, it's proving to you that the idea of superposition works. And theoretically, you could use this data, reinitialize in time, and it'll exactly retrace the original QT curve, actually shifted by the coefficient. But you could use shut-in periods to reconfirm where your transient stem ought to fit on your type curve, so you don't throw away the data. A lot of people they say, well, we're going to smooth the data, we're going to plot cum time and approach it that way. What you do is you end up throwing away your transient data. And it's easier to smooth the data by just taking a larger interval of time and getting the average rate over that time period and plotting it at the midpoint of the time period. It accomplishes the same thing. But I can think in terms and I can visualize the data a lot better in rate time than I can cum time. I can't think in terms of cum time. There's an example in there. I'm not going to dwell on this, but there's an example in the paper on the Inflow reservoir where we show the effect of a change in flowing pressure on an oil well. The well was originally flowing. Well, then the back pressure was changed, and then later it was put on pump. All we're doing here is using the concept of superposition. We've even introduced the ability to handle the flows above and below the bubble point pressure. Above the bubble point pressure is a delta P, below is delta P squared. This is nothing more than an expression in terms of real oil potential instead of the real gas potential, okay? Then the effect of actually the difference in pressure squared, the solution gas drive, and the effect that it has on lowering the flowing pressure to get an increase in oil rate. And we're doing all of this in terms of the ARCS equation. See, I don't have to use the rigorous analytic solution in terms of KH, skin, porosity, thickness, so on and so forth. We did the example, we're doing a superposition example in terms of the ARCS equation in terms of B, the Q sub I, and D. In the concept of superposition, that it's interesting to work through this example. Again, it's in the paper on a Inflow oil reservoir. It's this is the Federal A well in Wyoming. This is the original rate as a function of time at the original flowing pressure. This is where the back pressure was changed. This is nothing more than a change in the back pressure over the original shut-in pressure minus flowing pressure. It's a constant times that rate. This is the next back pressure change. It's a constant times that rate. So we're going back we're retracing the original QD-TD. But I've got to displace this rate to the time that it occurred. So I take this column, I move it over to here. I take this column at the time the back pressure was changed here. Then I go across and I add this rate plus this rate gives me the total rate as a result of back pressure changes. And the use or concept of superposition. You know, if you go back and look in production engineering practices by SPE, originally it was Frick's book, and now they've got it out. There's a real thick volume. There's a section in there how they used to do superposition for water influx. You know, it's nothing more than something very similar to here about the changes in the flowing pressure, and when they occurred. If I'd extrapolated the rate at the first flowing pressure, like as if it was going to act forever, I'd have got a cumulative recovery about 27,700 barrels of oil per day. By including the effect of the back pressure changes on a forecast, I was able to predict about 33,000. This is domestic. This doesn't mean much to you over here, but there's a big difference in results of extrapolating in, with the ability to use or to forecast the effect of a change in back pressure on your early time data when the well's flowing. So it can be done. This is a match of the actual performance on the well with the various back pressure changes. This is what it was doing at the first flowing pressure. That's what it would have continued to do if we hadn't changed it. This is the effect of the change in flowing pressure from 1,400 pounds to about 1,000 pounds, and then this was the effect that we you put the well on pump to try and determine how much ultimate reserve we were going to get from the well. That's the effect of putting it on pump in the extrapolation. I showed you earlier with the PD-TD. This is the QD-TD. I flipped it over. This is the infinite acting period down through here, and this is the depletion period. This period here is exponential decline. That's the single phase liquid solution, the analytic solution for constant wellbore pressure. Something you really have to recognize here is the concept of using effective wellbore radius, you know, the skin, with a stimulation. Echo-Fisk wells, I think you can get an RW prime of about 50 feet, Mike, would you say? Effective wellbore radius, about 50 to 100 feet for the skins we're getting. Okay, so that all else being equal, an unstimulated well, RW squared would be, you know, 0.3 times 0.3 would be about 1. Your 50 squared is a very large number in the denominator. Okay, same well. What that's going to do for you, it's going to push you way over here in your dimensionless time, which is going to, the potential, you're putting you in a period where you're going to be infinite acting or transient. We'll show you some of the Echo-Fisk area wells where it was actually in this period. You know, so you're going to end up in this period with low permeability stimulated wells. It's not enough it'd be low permeability. It's the negative skin for the effective wellbore radius that drives you over into this region where, you know, the rate time data becomes unique. And don't forget, it's K over mu. So low permeability, or a relatively high permeability oil with a very low viscosity, you could put you in a range where it would effectively act like a very low permeability system. Okay? And every time you introduce a transient, you're going to go back and retrace the QD, TD. It fits on a transient, or if it's going down depletion. There's a very big difference in the way the data looks log-log. But in the early days when we were in Bartlesville and we'd get data in from the international department overseas, the data come in on a telex. So you had a tabulation of the production rate versus time. And I can guarantee you a low permeability successfully stimulated well looks very, very bad in tabular form on a telex when management's the first ones to get it, and then the engineers get it. And the very first interpretation everybody makes is depletion. And it's very easy to plot the data log-log to tell if you're on a transient or if you're on a depletion. About the time I was working in this area, there was an article published first in the Tulsa World, and then later it showed up in the Oil and Gas Journal. And I was working in this area, and this is an article as it appeared in the Oil and Gas Journal, and you can see tests indicate limited reservoir at slope well. This is up there in North Slope. With declining flow rates during test periods indicated limited reservoir. What that means to me is it was being interpreted that it was depleting on test. And you could see in the first test they ran, the rate declined from 9,380 barrels per day. During a 16.5-hour test, the flow declined to 6,700 barrels of oil per day. What would you conclude if you saw that? Particularly if you was a boss. 2 years later, they came back and they retested the well. In 1977, similar results. They ran a little longer instead of 16.5 hours. They ran it for 96 hours, and the flow dropped to 5,000 barrels of oil per day. So it dropped almost in half in a 4-day period, a little over a 4-day period. If you take that data and plot it log-log, there's no question about what it is there? It's not depletion at all. It exactly fits on the infinite acting stem. And what looks bad said, hey, they got a very effective stimulation, because it requires a good negative skin to get that type of decay. So I can draw the conclusion looking at this data, and I'll show you the Edda well, one of the exploration wells, that a drastic decay in rate said, hey, they did a good job stimulating. But you know what the first interpretation was? Depletion. The next interpretation, it's a natural fractured system, so the fractures are closing. The next interpretation was, you see, we acid fracked all the early Ecofisk wells, no proppants. It obviously closed as a result of drawdown. None were applicable. Exactly fits the analytic solution. None of the exotic interpretations are applicable. It's very simply the transient behavior of a low permeability stimulated well, a very successfully stimulated well. Does everybody see that? You see how easy you can answer the question? But the other thing you got to remember, this is why you don't have anybody screw around with the choke. That rate time data is valuable if you just leave it fixed. I'll show you later that you can have a system where both the rate and the pressure are changing drastically at the same time. And if you take the pressure and the rate data and you normalize, exactly fit the analytic solution, because normalization is identically equivalent to rigorous superposition. Okay, so that's why you don't want to mess with the choke, because I can use that data. And again, there's a long period where engineers are going in there and jacking up that choke to keep it, because we want to make the build-up accurate. Yeah, because you need a constant rate before the build-up becomes accurate.